Welcome everyone to the next installment of TCS Plus. For those who don't know, TCS Plus is a long-running online seminar bringing you the latest and greatest in theoretical computer science, and we're always looking for suggestions for talks. So please feel free to fill out the Google form on the website. And today we are super lucky to have Rahul Ilango, who's a postdoc at IAS. Um, who'll be telling us about some really nice work on zero knowledge proofs, which appeared in Fox 2025. So Rahul, take it away.
All right, thank you very much. Yeah, so excited to be here at TCS Plus. Um, so uh, this, I think, is maybe the best toilet paper, I would say. It's very soft. I would say it has minimal chafing. I think, at least in my experience, this toilet paper is the best. Unfortunately, as good as this toilet paper is, it's kind of impossible to achieve, at least on a graduate student budget. And so, even though Charmin Ultra Soft is a fantastic toilet paper, the protagonist of our talk, which I have here, a version of, is not Charmin Ultra Soft. It's a Kirkland Signature toilet paper. And if you're not familiar with this brand, it's like this is a classic Costco brand where it's not the brand name toilet paper, but it's like kind of a generic toilet paper that is in some sense indistinguishable depending on what kind of adversary you are, and possible to achieve at least on a graduate student budget. So that's going to be the protagonist of our talk. We'll see Kirkland Ultrasoft later. Okay. So ideally, you guys would listen to all of my talk, and that would be great. But in case you don't, I thought I'd just tell you what I think like the two main takeaways are in this presentation. And the first is the result. And the result is saying that ordinary mathematical proofs, like the type of mathematical proofs that like Euclid wrote down, stuff that doesn't involve interaction or doesn't involve randomness, can hide secrets. So for example, you might want to be able to prove in maybe like the lean proof system or ZFC or something like that, give a standard mathematical proof that a Sudoku puzzle has a solution without revealing the solution. Okay. And so that the main result is kind of going to kind of say that this is possible. And the second takeaway I want you to take away is about the techniques. And the main technique in this result is being able to use unprovable statements, things that are true but like don't have a logical proof in cryptography. And kind of the idea is like maybe you have a cryptographic scheme which is insecure, but it's impossible to prove that that scheme is insecure. It turns out if you set this up correctly, what'll happen is it'll be like secure for all practical purposes. Okay, so
How is the first takeaway different from just zero knowledge?
sorry, the question was, how is the first result different from zero knowledge?
Yeah, your first
Yeah.
takeaway.
So I'll discuss this in more detail, but how this is different from traditional zero knowledge is traditional zero knowledge uses interaction between the prover and the verifier, where this is like an ordinary proof. You know, I can hand it to you, or you could write it down in a textbook, and yeah, great.
Okay, thanks.
Okay, so let's get started. And so like two of the big characters on our talk are going to be as follows. I just want to introduce them. So the first is the lean theorem prover. Okay, so I know hopefully I guess now in mathematics most people are familiar with this theorem prover. It's basically some software that lets you write down proofs in a way that like machines can check whether or not the proof is valid or not. And in this talk, I'll have to talk about a like logical system at some point. And just to make things as concrete as possible, I'll just always talk about the lean theorem prover. We won't need any properties about lean in this talk. Almost any proof system that you like, any logical system that you like, maybe ZFC or something like that, will suffice for our purposes. But I just want to be concrete. So let's fix this lean theorem prover. And basically, this is some piece of software that will take as input a statement and a purported proof of that statement, and either say, okay, this is a valid proof of that statement, or this is not a valid proof of the statement. Okay, so that's just some logical system. And then the second thing we'll need in this second main character in this talk is going to be this idea called a zero knowledge proof. Okay, and maybe a lot of you are familiar with the idea of a zero knowledge proof, and there's a lot of different explanations of what zero knowledge proof is. I'll give you my favorite explanation of a zero knowledge proof. So the year is 2017, and my two roommates, Tristan and Mikio, decide to go have some fried chicken. Okay, so they go to a restaurant, they're hungry, and they decide to order some Korean fried chicken. And what they do is they get soy, garlic, and spicy half and half. Okay, they go there, they order this, and they're excited. But when the food arrives, Mikio realizes three things that together cause kind of a serious problem. Okay, so what are the three things? The first is that the regular wings that they ordered and the spicy wings that they ordered look identical. The second thing is that the wings arrive all jumbled up on one basket. And the third is that the spicy wings are actually way too spicy for him. So because this actually happened, I actually have some footage from Mikio's predicament. So here is Mikio and the chicken wings. And actually in this video, he's saying,
I can't tell.
saying he can't tell, between the two types of wings. And he explains this to Tristan. And Tristan actually disagrees. He's saying, like, Mikio, what are you talking about? It's easy to tell the difference between the regular wings and the spicy wings. But Mikio doesn't believe him. He doesn't think Tristan can actually tell. Okay. So now Tristan decides he's going to convince Mikio that he can tell. And one thing he could do is he could explain, oh, if you look at the wings, you can see like these spice flakes over here or something like that. He could explain it that way. But he decides to try and convince Mikio that he can tell a different way. What does he do? He takes a wing, he puts it on Mikio's plate. Mikio takes a bite. It's spicy. Tristan takes another wing, puts it on Mikio's plate. Mikio, having just finished the spicy first wing, takes another bite. And guess what? It's spicy again. Now Mikio, his mouth is on fire from eating these two spicy wings, gets another wing on his plate. And guess what? It's spicy again. And at this point, Mikio realizes what is happening. Tristan can tell the difference between the spicy wings and the regular wings, and is purposely giving him spicy wings. So he admits, okay, fine, I don't know how, but you can tell the difference. Okay, so what has happened in this protocol? Well, what has Tristan done? He's like run this protocol where he sends a wing to Mikio, Mikio tastes it, and then sees that it's spicy. And at the end of the protocol, Mikio is convinced that Tristan can tell the difference between the spicy wings and the non-spicy wings. Why? Well, if Tristan couldn't tell the difference, then every time he sent a wing, the chance that it was spicy is going to be like 50%. And after three, iterations of this, like the probability he would be able to do this would be like roughly 1/8. And I guess Mikio doesn't care too much about soundness. At this point, his mouth is on fire. And he concludes that like, oh, 1/8 is too unlikely. Tristan must be able to tell the difference between the regular wings and the spicy wings. So this protocol convinces Mikio that Tristan can tell the difference. But perhaps what's most interesting about this protocol is what Tristan has actually revealed to Mikio. At the end of the protocol, what does Mikio get? Mikio gets 3 examples of spicy wings. Now, during the course of dinner, Mikio would have found 3 examples of spicy wings anyway. In fact, if he wanted to get 3 examples of spicy wings, he could have just himself tried spicy wings or tried wings until he found 3 examples of spicy wings. So one could argue that Tristan has actually revealed nothing to Mikio. Everything that he revealed, Mikio could have found out for himself. In particular, in this particular experiment, Mikio did not learn how to tell the wings apart after this protocol ran, and which of the wings left were spicy. So I sent these slides to Mikio, and he responded with this text. Uh, he says, okay, being the verifier is a painful life. Okay, so this example is supposed to illustrate this idea of a zero knowledge proof, where you want to prove a statement is true without revealing anything else. So, for example, you might want to prove that a Sudoku is solvable by handing over a proof that somehow hides what the solution to the Sudoku puzzle is. And at first, this like idea of like not revealing anything else seems like a slippery notion. Like how do you define not revealing anything? And one of the beautiful ideas by Goldwasser, Macaulay, and Rakoff, who define zero knowledge, is to define this idea via simulation. And kind of the idea is intuitively, if you know everything that someone else is going to say, like beforehand, before you have a conversation with them, you could write down everything that they were going to tell you. You're not going to learn anything by talking to them. You know, if you could predict in advance everything that they're going to say, then the conversation is not, you're not going to learn anything from the conversation. And you can make this into a formal cryptographic definition where you have like maybe some efficient algorithm called a simulator that simulates the conversation that the verifier and the prover have. But for this talk at this like kind of informal level of like if you know everything else someone else is going to say, you won't learn anything by talking to them is enough. Okay, so there's this beautiful definition of zero knowledge, and meaning that gives you some way to capture proving that something is true without revealing anything else. But maybe at first you might wonder that you might think that this is only possible for like very particular kinds of statements. Like in this chicken wing example, we needed like a really elaborate setup where all the chicken wings are shuffled and Mikio and Tristan are at a table together. It seems like at first you might think zero knowledge proofs are kind of rare. But amazingly, there's this result by Goldreich, Macaulay, and Wigderson, which basically says that anything you can prove, any NP statement, you can prove in zero knowledge under a basic assumption in cryptography. So zero knowledge proofs turn out to be extremely powerful. You can do lots of things with them, and in fact, like they're now like a cornerstone primitive in a lot of cryptographic protocols. So they're amazing. Zero knowledge proof is great. Unfortunately, as amazing as they are, they do come with some costs. Okay. So what are two drawbacks of zero knowledge? So one drawback present in zero knowledge proofs is imperfect soundness. There's like some sense in which you can prove false statements. So for example, in this Tristan Mikio example, like maybe Tristan was just lucky. Every time he sent over a wing, there's this 50-50 chance that he sent over a spicy one, and Mikio might be convinced at the end that something is true when it's not actually true. So they usually, all existing zero knowledge proof systems offer probabilistic soundness, but not like perfect soundness. And the second thing, which is maybe more of a drawback, is interaction. Usually when we talk about proofs, they're like something you can take and you can write down and put in a textbook. But these proofs are not like that. They're like they require the verifier to be able to ask questions to the prover. And in this Mikio and Tristan example, you kind of needed this like elaborate setup where Mikio sees that Tristan is picking an untasted wing from the pile. Like if Tristan could only like send a letter to Mikio and had to convince him he could tell the difference, that seems much more difficult. And so a natural dream result is trying to get zero knowledge proofs without these two costs. Okay, can you get zero knowledge proofs with no interaction and perfect soundness? And this is a great dream, but the only problem with it is that it turns out to be impossible. Okay, so the Goldreich and Orange showed that, in fact, the definition of zero knowledge, this definition of having a simulator, is kind of inherently incompatible with no interaction and perfect soundness. And okay, so what does this mean? It means like, okay, maybe this dream result is impossible. Does that mean like we should kind of give up or like move on? Well, actually, impossibility results in cryptography are kind of fuzzy notions. Like For example, kind of the first result in cryptography ever, Shannon's result on information theoretic encryption, said that in some sense, encryption is impossible. Yeah. But later, people realized, if you use a different definition of encryption that's just as good for all practical purposes, then we can actually achieve that. Okay, so maybe with this dream result, like the initial definition is impossible, but there is some other definition uh, of zero knowledge, just like there was another definition of encryption that we can achieve. And there's been several attempts towards this, but even some like simple cases, things you'd really want, stuff like what's called a witness hiding proof, we didn't know how to construct. So in a witness hiding proof, you want to prove, let's say, that a Sudoku puzzle is solvable without revealing a solution to it. And like a good example to think of, concrete example is like maybe witness hiding for factoring. Let's say I come up with a random product of two primes, x equals p times q, and I want to prove to you that, x is a product of two primes without revealing what those two primes are. So I could just send over to you p and q, but then you would know p and q. Like, is there some way I can convince you that this is a product of two primes without revealing what those two primes are? Okay. And there is even some sense in which maybe it's like impossible to, achieve this dream result. Here's a quote from Barak Angbadan. It says, given the possibility results, reducing interaction further seems unlikely. Indeed, in a truly non-interactive setup, in a truly non-interactive proof, it seems to be inherently incompatible with the intuitive notion of zero knowledge. From such a proof, the verifier gains the ability to prove the same statements to others. So what Barak Angbadan are saying is there's kind of this attack on truly non-interactive zero knowledge, where if I hand you a proof of a statement, you can replay that proof. Like if you hand me the proof of a statement, I can copy and paste it and give it to somebody else, and that seems to be intuitively violating what you would want out of zero knowledge proof. And it turns out there's like a slight flaw in this, and that's what part of what we'll exploit in this result. But you can think about that a little bit. We can come back to it later. So there was this intuition that like it might be hard to bypass the possibility results of Goldreich and Oren. It wasn't totally clear how to get around this. Cryptographers actually moved to a different model. So there's this thing called NIZK, non-interactive zero knowledge, and there they assume that like the prover and the verifier have access to some string sampled beforehand. They both have access to kind of shared randomness. And in this model, which you can get some version of non-interactive zero knowledge, but for this talk, we don't assume that the parties have access to any trusted setup or anything like that. Okay. Okay. Any questions about this zero knowledge stuff or yeah, background? Cool. All right. So how are we going to get around this? Seems like we're going to need a new idea, and this is when we enter a new character. Okay. So Shivam, who do you think this guy is?
I think it's Hilbert.
Yeah, good. Okay, it's a bit of a trick question because people usually sometimes think this is Gödel because it's that, but this is actually yeah, good. This is actually Hilbert. And so Hilbert had many dreams, but like one of the dreams that he had was like to come up with some formal system for math where like in that system it would be complete in the sense that for every statement you could either prove it's like true or false. And he was like, we should really come up with some formal logical system for arguing statements about the natural numbers, which has this completeness property. And this will be great. But unfortunately for Hilbert, Gödel showed that like this dream is impossible. In fact, it's like he showed that any such system which satisfies kind of these first two properties also has to prove 0 equals 1, which is not what you want from your system. Okay. So what exactly did Gödel prove? So Gödel proved that in whatever logical system you choose, for example, the lean proof system, which we talked about earlier, there are statements that are true, but that do not have any proof. Okay. And so let me give you a couple examples. So one example, which comes from his second incompleteness theorem, is about consistency. Okay. So the statement is X is that lean never proves 0 equals 1. Okay, so the statement is that you can never come up with a proof that the lean proof system will interpret as a valid proof of 0 equals 1. And so this is saying lean cannot prove its own consistency. And lean can actually talk about lean because, lean is just some computer program. And so you could give me the code for that program and ask, does this program ever accept a proof of 0 equals 1? So that's one example. Another example, which is kind of crazy, it's due to Chaitin, it's called Chaitin's incompleteness theorem, is that statements of the following form are unprovable. Let's say you want to prove that like no 100-bit Python program outputs verbatim the Declaration of Independence. Now, probably all of you agree, or most of you agree, that like there's not going to be a 100-bit Python program that outputs the Declaration of Independence. Nevertheless, for sufficiently large values of 100 and for sufficiently complicated declarations of independence, this statement is actually unprovable in lean. You might think, oh, let me just enumerate over all 100-bit Python programs, evaluate them, and see that they don't output the Declaration of Independence. But how are you going to tell whether a program halts or not? It was the problem you run into. And so, like, these unprovable statements, they made Hilbert sad. But in this talk, I want to tell you that why incompleteness is kind of a good thing, and why Hilbert's loss is cryptography's gain, and maybe your gain as well. Okay, so what's good about incompleteness? What is the joy of incompleteness? And now we come back to our protagonist, which is Kirkland Ultrasoft. Okay, so one consequence of Gödel's result is the following. Like, let's say you have a statement X that you really like, that you're interested in. For example, that the number 1, 2, 3, 4, 7, 9 is prime. Because of Gödel's incompleteness theorem, like you could think of Gödel as almost like opening up like some sort of Costco, where now you can take your statement X, any statement you like, and relax it in a certain way. In particular, you can relax it to a statement X tilde, which says that lean cannot prove that X is false. So to make this more concrete, like X tilde would say, lean cannot prove that this number is composite. Okay, so I'll give you like 10 seconds or like a couple seconds to kind of process this. But we're going to go through some examples. But yeah. And kind of what I'll argue in the next few slides is that, X tilde is kind of a weaker statement, but it's not much weaker.
Rahul, maybe I'm a little confused. I thought the incompleteness theorem says that there exist statements, right? So you can't plug this, you can't like choose any X of your choice here, right?
Good. So incompleteness theorem says there are things that are true, but that you can't prove, right?
Right. Yeah.
And what I'm saying is what's good, okay, so that's one thing. You take that and put it to the side. And I'm saying, okay, now let me say that let me, say for any statement X, I can create a new statement X tilde. Now you might argue with me saying like, is X tilde any different from X or something like that? And Gödel's incompleteness theorem will say that like, at least for some statements, X, and X tilde are different. It is true that for many statements, as we'll see an example of very quickly, that X and X tilde actually are the same, but Gödel's incompleteness theorem says at least in some of these cases, this is X tilde is a relaxation. Yeah, great question. Any other questions? Okay, good. So let's go through an example, and I want to zoom in on this particular primality example. So we have this number, or we have this statement that number 1, 2, 3, 4, 7, 9 is prime, and the X tilde version of it. And actually, yeah, okay, I guess Shivam, because you're the guy participating, I guess I'm gonna have to call on you always that you made the mistake. Yeah, can you tell me something interesting about this particular X and X tilde, like uh, maybe related to your question earlier?
X is not prime.
Good, good. Oh, okay, I think what you're saying is like in this case, X and X tilde are actually just the same statement, right? Um, Why is this? Well, if it so happened that this number is not prime, you can prove it's not prime. You'll just hand me the two factors of the number, and then I can check for myself and see that they multiply to this number. Okay? In particular, primality is a property that I'll call falsifiable, kind of hinting at this notion of falsifiability in cryptography, in the sense that if this statement is false, then there exists a proof that it's false. And so primality is falsifiable because if something is not false, I mean not prime, then you can prove to me that it's not prime. Okay, and we'll call such statements falsifiable. Okay, good. So that's primality. Let's go to another example. And this example two is going to be RH. RH stands for the Riemann hypothesis. And this slide is kind of going to be my most important slide in some sense, because I kind of want to illustrate to you the core idea in the zero knowledge results while abstracting out all the cryptography involved. So I'm kind of trying to give you this like core nugget of the idea without any of the cryptography hanging around. And so I want to use this example like the Riemann hypothesis, which hopefully, you don't know anything about. So just will illustrate the core idea. Okay, so what is the Riemann hypothesis? For the purpose of this slide, you don't need to know anything about the Riemann hypothesis, except that it asserts that some function called the zeta function is not equal to zero on some set of complex numbers. Okay, the Riemann hypothesis says there's a particular set, and it asserts that the Riemann zeta function is not equal to zero on that set. And once you get this x, now we have our x tilde, which says that you cannot prove that the Riemann hypothesis is false. Okay, now, a priori, you might expect that the Riemann hypothesis is not a falsifiable statement. Why? Well, if the Riemann hypothesis is false, it means that there's some complex number on which the zeta function evaluates to zero. But a complex number requires infinite digits of precision. So maybe a priori you might think Riemann hypothesis is not falsifiable. I mean, it turns out there's some complex analysis stuff you can do such that you can make it falsifiable, but for the purposes of this slide, let's pretend Riemann hypothesis isn't something that is falsifiable. Now, I'm not a complex analyst. Like, do I really care about the zeta function itself? I mean, I don't know. I mean, it's intrinsically interesting, but what I really care about is not the zeta function itself, but it's like consequences on the prime numbers. In particular, like the Riemann hypothesis has falsifiable consequences about the prime numbers. If the Riemann hypothesis is true, then there's always going to be a prime number in any interval of size roughly square root n. Okay? So the Riemann hypothesis implies facts about prime numbers, and in this case, this fact about the prime numbers is something that is falsifiable. Why? Suppose there was some x for which there was no prime in this interval, then how can I prove to you that that's the case? Well, for every number in this interval, I could just hand you the two factors of that number. And I've proved to you that this consequence is false. Okay, good. So the Riemann hypothesis has some falsifiable consequences. And now what I claim is that if RH tilde is true instead of RH, then we should also get this falsifiable consequence. So I'll call this consequence K. K is for consequence. I already used C for the complex numbers. And I claim if RH tilde is true, then we also will get this falsifiable consequence. And why is that? It's a simple proof by contrapositive. So it's a proof by contrapositive. So we start with not K. And once we know not K, we'll know that lean proves not K. Why? This is the definition of K being falsifiable. Once we know that lean proves not K, then we'll also know lean proves not Riemann hypothesis. Why is that? Well, we know that not K is true, and then Deduc's result, which I'll assume can be formalized in lean, says that the Riemann hypothesis implies K. So once you know not K, and that you'll also know not Riemann hypothesis. And by definition, statement 3 is not RH tilde. Okay. So hopefully, yeah, maybe yeah. Does anybody have any questions here? Like in some sense, this is my most important slide where I'm saying like, when you take this tilde relaxation, um, it will still give you all the falsifiable consequences of your statement. And in particular, like this proof didn't use anything in particular about the this particular falsifiable consequence. In general, if x tilde is true, every falsifiable consequence k of x is true. Okay, any questions?
Rahul, is falsifiability it's tied to
Mhm.
lean over here, right? Like if you had like a
Good.
different system like Isabel or whatever,
Yep.
is
Yeah,
there,
yeah. So great question. Right now, I've defined falsifiability in terms of lean, but you can choose your favorite proof system and you can, yeah.
and is there a sense in which all of these are equivalent? Like the proof system does not matter, or is it?
Good. Good. The proof system will matter. Yeah, we'll see this. In fact, that'll actually be one of the assumptions kind of in our, but we'll see. Once we come to zero knowledge, it'll be more clear exactly. Yeah. Good.
I think Ahmed has a question, or
Oh, yeah, sure.
Ahmed, feel free to unmute yourself.
Uh, can you hear me?
Yeah.
Yes.
Yeah. Sorry, maybe it's a stupid question, but does this say something that it's the only consequence of the Riemann hypothesis that so maybe you can prove something about the consequence that always prime in this range, but does it say that this is the only consequence, and does this make a difference?
What do you mean by the only consequence? Like,
Um, so it implies this, but
mhm.
then it also implies other things. Um, and then do you also need to prove these other things in order to do the counterpositive?
Yeah, so this claim will work for any falsifiable k that is implied by the Riemann hypothesis. So if you can prove that the proper Riemann hypothesis implies some falsifiable consequence k, then that'll also mean that the Riemann hypothesis tilde also implies the falsifiable consequence k.
Yeah, thank you.
Yeah. And now, hinting back to like we're going to try and use this in cryptography, like why might this be useful in cryptography? It turns out in cryptography, almost all definitions you can make are falsifiable with a star. And so on the next slide, I'll explain what that star is. Okay. So in this slide, I'm going to try and tell you a little bit about like why a lot of assumptions in cryptography are falsifiable. And for that, I'm going to have to use an example of some object in cryptography. One of like the key objects and main objects in cryptography is something called a one-way function. And when people define one-way functions, they usually talk about asymptotic security. But as I'll talk about here, you can talk about instead of asymptotic security, you can talk about concrete security. So for example, you could say that for every n and for every circuit adversary of a particular size, the probability that that adversary inverts f on a random x is at most, let's say, 2 to the minus square root n or something like that. So you can choose a particular security value, and then you could define a one-way function with respect to that concrete security function. And usually in cryptography, they don't try and say they'll say like, oh, this is sub-exponentially secure or like super polynomially secure, but you could always, trade that for particular security function. And once you do that, this is something that is falsifiable. Why? Well, if I want to prove to you that something is not a 2 to the square root n secure one-way function, what do? I'll just hand you the n and hand you the adversary of that size, and then you could go in yourself and evaluate this circuit on all the possible x in order to compute this probability and see that this adversary breaks this guarantee. In fact, if if you believe in some de-randomization assumption, this actually has a proof of like polynomial in your whatever security function you choose. And for, a vast number of properties in cryptography, or sorry, objects in cryptography, one-way functions, pseudorandom generators, encryption, even indistinguishability obfuscation, and this example that I mentioned earlier, witness hiding for factoring, as long as you choose like some concrete security that you want, they're all falsifiable definitions.
Sorry, this is all in the lean proof systems.
Yeah, although
It doesn't matter.
Yeah, as long
I'm
as you
just
have
curious. I don't know much. Has anyone verified that these things are actually that these proofs actually carry through the proof systems, like the lean system? Has this been claimed
sorry.
somewhere?
Yeah, so which proofs are you asking if they've been
For
formalized?
example, the search for the one-way function inverter, that so you're claiming that somehow this stuff that you're saying of like going through every input and checking this can be formalized in lean, right?
Yeah, it can be formalized, yeah.
Is this sort of like explicitly written somewhere, or
I guess it's not explicitly written somewhere,
right?
but yeah, I mean it's just like lean can do. All right,
Can
yeah,
do everything.
yeah. I think you have to work really hard. I don't know if there's anything that's like maybe there are things in like category theory or something that like can't be formalized, but like anything that talks about sets, unless you're doing something really crazy, you can formalize.
But also, I guess when you um, do these things, you have a fixed n in mind.
Good, very good
So really,
question.
I mean, there really isn't anything. I mean, every statement about fixed numbers can be proved, like in extremely weak systems, like
Yeah, yeah,
right. So
yeah,
you
yeah,
don't
yeah.
just
Good, yeah,
okay, all right,
yeah.
fine. So
Yeah, just
this was
choosing lean
happening,
to
like
make it concrete. Yeah, yeah.
yeah, very good. Okay.
Okay, good. So just to recap what I've said so far, one thing that's good about incompleteness is it gives us like this general way to relax any statement X into statement X tilde, where X tilde could be weaker, but like not much weaker. And that's great, but like, is this X tilde useful in some way? Well, here's an idea. Maybe you want something like X to be true, but it turns out that it's false. Maybe you can just use X tilde, which hopefully is true, and that'll be just as good in the sense that if X tilde is true, then like you get all these falsifiable consequences, which is maybe all you cared about. In particular, this is kind of one way to interpret this is like some sort of distributionless version of computational indistinguishability, in the sense that like if you can't prove that some statement is false in some quantitative way, then it's indistinguishable from true. And, and at least if you care about the falsifiable consequences, which is most of what you care about in cryptography, that's hopefully good enough for you. Okay, and so this idea is very general, and you could imagine using it in many different settings, not just cryptography, but complexity theory or theoretical computer science, or even mathematics more generally. But in the rest of the talk, I'm going to tell you a little bit about how you use this to get this zero knowledge stream result. And when we do that, actually, we're going to have to be a little bit more quantitative, and we'll need a more quantitative version of X tilde and a more quantitative version of falsifiable. So things will get a little bit more complicated. I tried to abstract things out so far in what I've told you so far, but yeah. Okay, so before we switch to zero knowledge, any questions so far? All right, great. All right, so now let me tell you a little bit about this result. So I'll say informally what it is first, and we'll say it a little bit more formally. So the informal theorem is that zero knowledge with no interaction, no setup, and perfect soundness is effectively possible. And on the next few slides, I'm going to tell you three things. I'm going to tell you a little bit about what the formal definition of effectively is. Then I'll tell you a little bit about how you construct it. And then I'll say a little bit about why it's useful. So that's what we're going to do next. Okay, so first, what is effectively zero knowledge? Well, before I tell you what effectively zero knowledge is, let's review what classical zero knowledge is. And the classical definition of zero knowledge basically says there is an algorithm that called a simulator, and it has particular property. That particular property is this idea that if like you can predict what's everything that somebody else is going to say in advance, then you won't learn anything from them. And the simulator encodes that, but actually for this slide, you don't even really need to know what a simulator guarantees. Zero knowledge definition says that there is an algorithm called the simulator. It has some property, whatever. So that's a classical definition. So what is effectively zero knowledge? It says it's hard to rule out that a simulator exists. Okay, and you should think of this as kind of like this tilde version of zero knowledge. In particular, what'll happen is the requirement is that any lean proof that no simulator exists on input length n. And for here, I want you to put like a particular number n here. So like, for example, no simulator exists on input length 1000. If you want to prove that no simulator exists on input length 1000, then the shortest proof of that will have super polynomial size, or here I just put a concrete number like 2 to the n to the 0.01. Okay, so this is some way to quantify, like not it being difficult to rule out that a simulator exists. One question you could ask is like, what does it mean for no simulator to exist on input length n? If you're familiar with the definition of zero knowledge and what a simulator is, I put a little bit more formally what that means. Like you'll have to pick a particular circuit size for the simulator and a particular indistinguishability that you want to have, but you can kind of write that down. And also in this definition, I made this choice of logical system, which is this lean proof system. You can choose whichever proof system you want. Yeah, the definition is parameterized by choice, but yeah, just to be concrete, I'll talk about lean. Okay, questions about the definition?
Do you know unconditionally if the simulator exists or not, regardless of the probability?
Regardless of the probability, do you know?
Regardless of the probability.
Oh, provability, good.
Yeah.
Okay, so for the construction for our construction, the simulator will not exist.
No exist.
But it's hard to prove that there's no simulator. Yeah, good. Okay, great. So now I'll say a little bit about how you construct this object. And now I'll be able to say a little bit more formally what the theorem is. So the theorem is that for every logical system, so for example, the lean proof system, you can get a prover and verifier for SAT, which has perfect soundness, which is truly non-interactive, and which is effectively zero knowledge with respect to that proof system like lean, under two assumptions. One is an assumption in cryptography called, it's NIWIs exist. NIWIs stand for non-interactive witness indistinguishable proof system. If you're familiar with it, if you're not familiar with it, it's just something that follows from various standard assumptions. And the second assumption is an assumption in proof complexity. In fact, you can think of it as some sort of like scaled down version of Gödel's incompleteness theorem. But this is a conjectured scaling down of Gödel's incompleteness theorem. And just to say a little bit about this second assumption, because it's an assumption in proof complexity, not in cryptography, here's a quote from Krychek and Pudlak, who conjectured this thing in 1989, which ironically is like the same year as zero knowledge was published in journals. And it says, like, if an optimal proof system exists, we could realize the Hilbert program. They're talking about Hilbert's second problem here, I think. In a modified finitistic sense, we conjecture that this is not possible. It's also like an assumption that like proof complexity people have studied a lot. And for example, on the Wikipedia page for proof complexity, it's like one of three main problems that are mentioned on the page. So this is like a assumption that's pretty a foundational assumption in proof complexity. And when you look at this theorem, you might wonder like, okay, I'm getting some cryptographic results and like I had to use some ideas from proof complexity. Like maybe, I mean, that's cool, but maybe there's some way to do this using just cryptography or something like that. And one thing that's interesting is actually both of these assumptions are necessary. So like if you want to do zero knowledge without interaction, you necessarily like need this proof complexity assumption to be true, which is kind of I don't know, surprising, at least to me. Okay, so that's a little bit about the theorem statement. One thing that I want to mention is there's kind of like a for all exists flavor to this theorem. Like it says like if you pick a logical system, then I can hand you a prover and verifier that's effectively zero knowledge to that. You might hope that there's just a prover and verifier that's effectively zero knowledge to every logical system. It turns out that's impossible because of some version of the replay attack. You can kind of upgrade the replay attack, assuming that assuming an optimal proof system exists. But we actually get like a candidate prover that we conjecture has every natural falsifiable property of zero knowledge. So we have a concrete explicit candidate which we think, gets every natural falsifiable property of zero knowledge. Okay. So now let me tell you a bit about the construction. That's the theorem.
Are you going to
So,
say more about
oh,
this conjecture improved complexity, or this is it?
oh, sorry, what was the question?
Are you going to say more about this conjecture improved complexity, or this is it?
You'll see a little bit more on the next
Okay.
slide. But I do have some bonus slides later if you want to hear.
Okay, because it's, I mean, it's okay. It's
Yeah. Okay, so what is the construction? So let's say you're the prover, right? You want to prove that, let's say, a Sudoku puzzle is solvable. What do? So the construction, which builds on this work by Feige Shamir, Feige Lapdot Shamir, Barak Angvadan, and Quick-Kendall and Zandri, and it works as follows. The prover is not going to prove to you that the Sudoku puzzle is solvable. Instead, the prover is going to prove some other thing. What is that other thing? He's going to prove to you that if some statement X is true, then the Sudoku puzzle is solvable. And this statement X will have nothing to do with the Sudoku puzzle at all. Okay? He's going to say, I'll tell you if the statement X is true, then the Sudoku puzzle is solvable. And what we'll do is we'll choose the statement X to be like a Gödel statement, which is like true, but unprovable. Okay. So for example, a good thing to keep in your mind is maybe this like consistency thing, where if the statement X is that lean is consistent, which means it never proves 0 equals 1. If that's helpful for you, you can think of that. All right, so the prover is going to say if lean is consistent, then the Sudoku puzzle is solvable. And what's good about this construction? Well, because we picked a statement that is true, this proof that the prover is handing me is actually like useful. It's saying that like because X is true, I now know the Sudoku puzzle is actually solvable, and this gives me perfect soundness. But lean, since we chose a statement that's unprovable, lean can't tell whether X is true or false. And if X were false, then the proof that the prover presented is actually vacuous, like he's proving that like if a hypothesis which is false holds, then the Sudoku is solvable, but like that proof is vacuous if the hypothesis is false. And it turns out you can use some cryptographic shenanigans, like a very clever idea coming back to Feige Lapdot Shamir, and this assumption that NUIs exist to show that like actually this proof will be zero knowledge. So and kind of the intuition is like if X were false, then this proof is vacuous. And so you can do some cryptographic machinery in order to make that proof zero knowledge if it were false. And this is what's going to give us this like effectively zero knowledge guarantee, because we're saying you can't rule out that this is zero knowledge. Okay, good. And actually, things are a little bit more complicated than this. Like you can't use the statement that lean is consistent because that talks about like potential proofs of 0 equals 1 of unbounded length. It turns out like in order to make use of the cryptographic machinery that we need, you need this statement to be something which is like has potentially like a finite, which goes over a finite number of proofs. So actually the statement X that you could consider maybe is like lean is consistent on proofs of length up to n. And this is where this assumption that there's no optimal proof system kind of comes in. Okay, questions about the construction? Okay, good. And now, so I'll say a little bit about using this assumption. So it turns out this suffices for almost all the applications of classical zero knowledge in the literature, pretty much any application that doesn't like explicitly mention the word simulator, all of these falsifiable consequences. But just to give an example, like we can come back to this witness hiding for factoring thing. But one caveat, which I maybe hinted at already earlier, is that you don't get like one universal prover that works for essentially all applications. Like the prover potentially might change. Um, but the reason why like we get all these applications is as follows. The idea is like, okay, let's look at witness hiding for factoring, right? Let's suppose, there was an attack on our system, on our effectively zero knowledge system. So there's some successful attacker that on input length 100 gets a proof that, X is a product of two primes and is able to extract from that proof a P and a Q. And I want to emphasize like this attacker has finite size. It's like a circuit, and this like input length is finite. And so if this is like a polynomial in 1000 size circuit that is doing this attack, this attacker is in some sense a certificate ruling out that our proof system is zero knowledge on this particular input length. And basically we've set everything up so that this is exactly breaks our guarantee. This adversary is certifying that that our prover is not zero knowledge and that there is no simulator, and that's exactly what we said was not possible. Good. So the idea is basically any attack on the system is a certificate that we weren't zero knowledge. And we kind of set things up so that you shouldn't be able to certify that it's not zero knowledge. But I will say there are like two things that I'm kind of assuming here. One is that you need to assume that factoring is hard, because obviously if factoring is not hard, well then given X, I can just find P and Q myself. I don't even have to break the proof. And actually, you need that Lean can prove factoring is hard in order to carry this jump from the adversary A existing in order to get to breaking the guarantee. And so, you might wonder, like, what if Lean can't prove that factoring is hard? Maybe you're a lower bound skeptic. I mean, I'm a complexity theorist, so my dream is that all these lower bounds are provable. But maybe you're a lower bound skeptic. You don't think that we should be able to prove circuit lower bounds, or maybe it might be hard. So then you actually will have two options. One option is just add hardness of factoring as an axiom, basically, to Lean. And so the prover will change. It'll become like one candidate prover is that like now if Lean plus factoring is hard, has some finitary consistency statement, then the Sudoku is solvable. You can change it like this. But the downside here is now your prover has maybe changed, which is why we don't get this universal prover. Another option you can do is there's like a heuristic leap you can make. Maybe you can stick with this original prover, which said like if Lean is consistent on proofs of length n, then the Sudoku is solvable. It turns out the analysis for this still works as long as knowing that factoring is hard doesn't help Lean prove its own consistency. And like a not formal conjecture we make in the paper is that for any natural cryptographic assumption, it doesn't help Lean prove its own consistency. Yeah. So, and this is how we get our candidate prover, which we think has all natural falsifiable properties of zero knowledge. Okay, so that's what I want to tell you about the main result. I told you these three things, like a little bit about how you define effectively zero knowledge, a little bit about how you construct it, and a little bit about how it's useful. And so here I have a little illustration of the idea of effectively zero knowledge proofs. You can't prove it's not zero knowledge. And I just want to conclude with some interpretations about the result. One interpretation about what's happening is that what I mentioned before is this idea of like indistinguishability without a distribution. If it's hard to rule out, this should be hard to rule out that not X. I forgot, I dropped the negation. But if it's hard to rule out that X is false, then in some sense it's effectively true. And if you only care about falsifiable consequences, which is usually what happens in cryptography, then that's good enough. Another interpretation is about like proof theoretic relaxations, which is like if you have a definition, like for example, the definition of zero knowledge, you can maybe try and like relax its requirements and to only hold on like proof theoretically interesting consequences. Oh yeah, so let me say that again. So like in some sense, this definition of effectively zero knowledge says uh, I'm going to require that all the consequences of having a simulator that have some nice proof theoretic property, in particular, they're like falsifiable, um, will hold. I don't require that every consequence of having a simulator holds, just these falsifiable ones. And that gives you like some proof theoretic relaxation of a definition. And in fact, this is like not a new idea. There's this work going back to Abhishek Jain and Zhenjiang Jin, which also relax the idea of indistinguishability obfuscation, where you have some guarantee that it holds, where only certain consequences that are proof theoretically interesting hold. Um, Although one thing that is different about this work compared to their work is that they're mostly using proof complexity upper bounds, where here we're using unprovability as an assumption. And the last thing is like usually in computer science, we think about like time as a resource, space as a resource, and stuff like that. I think the one thing that's illustrated in this work is that like axioms are a resource you could potentially exploit when you're trying to do something. And like in some sense, the way that we get around this impossibility result for zero knowledge, there's kind of this like tension between um, having soundness and having a simulator. And what we can do is we can like avoid these attacks by like kind of not giving the security definition enough axioms in order to talk about the attack, if that makes sense. Anyway, so in this talk, there was this impossibility result. You couldn't do zero knowledge without interaction, and we showed that you could actually do that. And what I'm excited about for the future is what other false theorems can we prove. All right, thank you very much. Oh, I should also say that like this idea of using unprovable statements in cryptography, it's already finding some applications. So there's this very nice paper that is using it to try and to build snarks for NP. Yeah.
Rahul, can you say a word about how this corresponds to the BOV limitation argument? I mean, the saying
Good.
you take
Yeah,
something
very good.
constructive, now I can prove to someone else. So it seems like I've learned something.
Yeah, very good. Okay, yeah. So there's this, BOV pointed out this attack, which is this replay attack, where if you hand me a proof, I can copy and paste it, hand it to somebody else, and they're saying, that seems to intuitively violate zero knowledge. Okay, so the way we avoid this is actually really subtle. Um, so let me just try and illustrate to you a little bit about why the replay attack is so subtle. So here is a proof system I want you to think about. It's like a really silly proof system. Imagine the prover is given some statement and a witness to that statement, and they just ignore both of their inputs and they output 0 to the n. Okay? So this is a really, bad prover in the sense that like it doesn't have soundness. It didn't do anything with its input. And yeah, so soundness is bad, but zero knowledge is great, right? Like it didn't do anything. Like I can predict everything that it has a simulator that's amazing. It's just like simulators here. And nevertheless, despite this thing being kind of like the best zero knowledge proof or zero knowledge, having the best zero knowledge property you could want, you can still do the replay attack on it. And so then what that says is that replay attack, it's not quite an attack on zero knowledge. It's like an attack on zero knowledge plus soundness. And what will happen in this construction is that, yeah, let me go back to the construction. In this construction, there's kind of like these two cases, either X is true or X is false. If X is true, you'll get perfect soundness. If X is false, you'll get a simulator. So like you won't know whether you're sound or whether you're have a simulator. And so then like because the replay attack requires both soundness and a simulator, or sorry, yeah, the replay attack is like some combination of like soundness and zero knowledge. That's the or the replay attack is violating some kind of combination of soundness and zero knowledge. Yeah,
Yeah, I see. Thanks.
yeah. Another way you could also think about this is like, what's the okay, maybe I'll end there because it's a little slow. Yeah.
Rahul, so the construction also makes it clear why the prover depends on the proof system, why it depends on lean, but does the
Mhm.
verifier also depend on?
Good. So um, the verifier will need to know what the statement X is. Since the statement X depends on lean, like, so what will the verifier do? Yeah, okay, good. Uh, yes.
So like on the next slide, when there's these two options,
Is
I
this
mean,
where, is this what you mean? Oh, okay, these two
yeah,
options.
yeah, yeah. So I think the verifier needs to know.
Yeah, we'll need to know what assumption, well, either what thing you added as an axiom in this case.
Right,
Actually, in option two, the verifier doesn't need to know
right,
what
right, right. Yeah, but in option one, I would need to know.
in option one it would need to know. Yeah. Yeah.
Can you say more about this conjecture improved complexity that you're using?
Yeah, yeah, good. Let me go to that bonus slide. Good. Okay, one second. I think I have to unhide that slide. I'll just uh, oh, okay, yeah. Sorry. All right. So this is this conjecture about no optimal proof systems. It was by Krychek and Pudlak in 1989. And it basically says that or there's a couple ways you could phrase it. One way you could phrase it is the following. For every proof system L, so if you think lean here, for example, there is like a uniform sequence of co-NP statements, X sub lambda, or yeah, I guess in this talk I was using N instead of lambda, but you can think of lambda as N. And so these statements are all of the form that like some circuit is unsatisfiable, and they're P uniform in the sense that like if you hand me 1 to the lambda, there's a particular Turing machine that will spit out the name of this co-NP statement, and that co-NP statement requires super polynomial length proofs in lean or your favorite proof system. And like actually in the paper we need this to hold in for infinitely often. It's like one of these things like if one-way functions exist, you actually need like SAT is hard for P infinitely often. Yeah. And just as comparison, like one way to think about this is like as some sort of strengthening of NP not equal to co-NP. So NP not equal to co-NP says, if you hand me a particular proof system like lean, there is a sequence of unsatisfiable formulas which require like large lean proofs to prove that they're unsatisfiable, but it doesn't guarantee like that there's like a uniform sequence of these guys. It's promises that these exist for every input length, but it doesn't tell you that you can, produce on this input. Like there's an efficient procedure that on given an input length will give you a hard co-NP statement. And like an explicit candidate, which is kind of what I was using um, in this talk, was like this finitary consistency, which is like there is no lambda length proof of 0 equals 1 in say ZFC or lean, something like that. Which you can think of as like a scaling down of Gödel's incompleteness theorem. Actually, I'm lying a little bit here because, but okay, maybe I'll only tell you what I'm lying about if you're interested.
Um, I'll stop the recording now, and we can take more
Sure.
questions offline.
Yeah.
But thanks again, Rahul. Yeah.
Thanks for having me.